Hello everybody. This week we are going to look at n-gram language models. You will see that this is actually quite simple, but then it's also quite useful in the area of text mining or natural language processing. By the way, if you are experiencing any difficulty during this learning from home period, feel free to send me an email or something, okay? So as I said before, n-gram language models are actually quite simple, yet useful. In this presentation, we'll first see the possible applications of n-grams, and then we will see how it works. So think about it. We have a sequence of words, and then we're going to predict or guess what is the next word. For example, the sequence says, all of a sudden, I noticed tree something. N-gram language models may be useful to predict the next word from the previous n-1 words. So let's look at what n-gram means. So n-gram means that if you're having a 2-gram, or we usually call it as a bigram, it means that you're having a pair of words. It's almost like the sliding windows in the word embedding topic, if you remember about it. So here the bigrams are all of a sudden, and so on. We may also have a trigram, which means we are now looking at 3 words together. So all of a sudden I. And then if we are going to use these models to predict the next word, if we use bigram, means that we are using the word all to predict the word of. We are using the word of to predict the word and we are using the word to predict the word sudden. In trigram, we are using the previous 2 words to predict the third word. So all of to predict of to predict sudden, and then a sudden to predict I. And then what does language models mean? Language model means it is statistical models of word sequences. I bolded the word sequences because previously in vector semantics, we didn't really talk about sequence. We just look at each word one by one and then represent them as vectors. As the opposite, in this topic, we're going to take a look at sequence and we are going to put a lot of importance in the sequence of words. Sometimes we're also facing a question, which sentence or which sequence of words is more likely? Here, I provided 2 sequence of words, and I'm going to ask you which one is more likely. Both sequences contain the same words, by the way. Now you might ask why we want to know which sequence or which sentence is more likely. Well, it may be useful for applications such as text generation. For example, you want to provide an automatic summary of an article. Or if you're running a chatbot, the chatbot should reply the questions with a good sentence. And then also you might need this when you want to do some speech recognition, handwriting recognition. So to recognize whether it is more possible that this word is this or this word is that based on the sequence of the words. It may also be applied to predict what we're going to look at in the search machine. So for example, I typed in best songs to sing, and then Google suggested some words or phrases that are likely to follow the ones that I've already input. Of course, this might be coming from the search history, but n-grams might also be useful for this kind of task because you are going to guess or predict what are the likely words or phrases that coming in next. And if those words are not likely, then you will not suggest them. It might be useful in machine translation as well. So if you're going to translate automatically, and then you're going to choose which translation is the most probable. So let's see here we have a Chinese sentence. So if we translate word by word, so 他 means he, 相 means to, 记子 means reporters, 介绍了 means introduce, 主要 means main, 内容 means content. But then if you look at this sentence, he, two reporters introduced main content, maybe you get the meaning, but it's not a very good sentence, right? So then let's say you have 3 proposals of the better translation of that sentence, and then we are going to ask which one is the most likely to be the best translation. Well, the first one is a bit weird in English because introducing reporters to a statement. It's just usually you introduce somebody to somebody else, or so introduce to a statement seems a bit weird. The second sentence says he briefed 2 reporters. Briefed 2 is not really English. So among these 3 options, the sentence number 3 seems to be the most appropriate, the most English. N-grams language models may also be useful if we want to check if a sentence is grammatically correct. For example, there are 2 sentences here, and then their mistakes cannot be identified by simply checking if a word is in the dictionary, because all words here are English words, so you cannot simply check whether this word is in English vocabulary or not, because the mistakes is in the grammatical aspect, not in the spelling aspect. So using n-grams, you might see that there are is more probable than there are. And then you might also use n-grams to say that the pair of has improved is actually much more likely to occur than the pair of words saying that has improved without D at the end. Now that we've seen the possible applications of n-grams, now let's take a look at how it works. The foundation of n-gram language model is computing P, W given H, which means we're going to compute the probability of a word W to appear given some history H. Suppose we have seen this sequence of words. Its water is so transparent that. So that is the history. Imagine it's something like you have typed in the search engine. And then W is the word that we're going to predict what word would be the next word after the history. So here, given the sequence that we have seen, its water is so transparent that, we are going to ask, what is the probability that the next word would be the? How can we compute this probability? Well, one of the approach is that we use the frequency counts from a very large corpus. Corpus means all the documents that you have in your data set. So to compute this, we simply count in the denominator, we count how many times we have seen the history. So we count in our documents how many times we see exactly this sequence. Its water is so transparent that. You count how many times this sequence appears. And on the upper part of this equation, you count how many times its water is so transparent that the appears in all the documents that you have. Okay, so it's simply, we can do this simply by counting. In the lower part here, you count how many times the history appears. And then the upper part, you count how many times the history plus the word that we are going to predict, how many times this entire sequence appears. So by counting means you're just checking how many times it appears in all the documents that you have. You may use the search engine to check how many times a sequence appears, but apparently the result is a bit weird for this because when I search, its water is so transparent that it appears 2,960 times. However, when the sequence is longer, its water is so transparent that it appears much more frequent than the previous one. Why I say this is weird? Because usually if you have a longer sequence, then it should appear at least the same or even less than the shorter sequence. So I cannot really explain why this occurs. So in the next slide, I'm going to come up with another example that makes more sense, at least to me. So here I'm trying to search the sequence of words, students whose first language is not. And then Google returned 292,000 of results. And then I added one word at the end of the sequence. So I said students whose first language is not Chinese. And then you see now the number shrinks a lot, significantly a lot compared to before. So when you say that you're searching for students whose first language is not, you get a lot of results. But then when you say specifically students whose first language is not Chinese, it becomes significantly less. And then when I simply add the word the at the beginning of the sequence, so I said the students whose first language is not Chinese, and then Google says no results found. So what I'm going to show you here is that even if we have a very large corpus like the entire Google search, sometimes when you want to check a particular sequence of words, it may not be found. Because remember, sentences and languages can be very creative. You can put these words to make a new meaning or to suit the context or whatever. So basically, sometimes it's very hard to count how many times a sequence appears. So what I'd like to show from this slide is that when we talk about count how many times a sequence appears, sometimes it's difficult. It is even more difficult when the sequence gets longer and longer because sometimes you just never see that sequence appear. I'm going to talk about how we can overcome that difficulty in counting the frequency of a sequence appears, but let's talk about this for now. We'll keep that topic for a bit later, and now let's take a look at something else that is actually related. So here I'm going to talk about the joint probability. We have seen before actually that sometimes we'd like to know the probability of a sentence or a sequence of words W. Means that we want to know how likely a sequence is. We've seen this in the example of machine translation. Remember that I asked you which among the 3 translations that are the most English, the best translation of the Chinese sentence. So actually that question is like asking how likely a sequence of words is. How likely those words is a sentence, you know. And that is called joint probability because we are looking at the probability of a sequence. So take a look at an example. Suppose we're asking, what is the probability of its water is so transparent? What is the probability of this sequence to appear in a document, in an English document, let's say? So again, we may think about computing this probability by counting the probability of its water is so transparent. But now, because we are asking the probability of this, in the denominator part, we have to count all possible sequences of 5 words, right? Because we have 5 words in the sequence, its water is so transparent. We have this specific 5 words. So when we want to ask what is the probability of these 5 words to appear, we must divide the count that we see these 5 words divided by all possible sequences of any 5 words in the world. Now, it's very difficult. It's impossible to count all the possible sequences of 5 words because sometimes new words appear and then sometimes people are creative in changing the words and so on. And so it's just impossible. So again, this is another problem with counting. Considering this problem and the previous one, we're next going to see a smarter way to calculate PW given H and then P of big W, which is the probability of a sequence of words. Let's formulate the joint probability a little bit in an equation. So suppose we have a sequence of words from word 1, word 2, word 3, up to word N. So sometimes it's also, this notation is used. So W from 1 to N means sequence of words from word 1, word 2, word 3, up to word N. Now, what is the probability of this sequence? Well, the first one, because it is a sequence, so we must say that first one is probability of word 1 itself to appear times the probability of word 2 given that word 1 has appeared before, and then probability of word 3 given that we have a sequence from word 1 to word 2. Remember, because it's a sequence, so the history we must keep from the beginning up to the n-1 word. So when you're asking what is the probability of word N to appear, we must say that given the history that word 1 up to word n-1 has appeared. And then we have seen before that if n is large, then this is difficult to compute because it is getting rarer and rarer to see those sequences in the corpus, right? If you have a longer sequence of words, then it is it is less likely to appear in the documents already. Okay, and then by the way, this symbol here means the multiplication. So you multiply each time the probability of word K, given that the history has shown you from word 1 up to word K-1. And we've seen that this is kind of difficult to compute. So the exact joint probability is difficult. What we can do is we are taking an approximation by using n-gram language models to approximate the joint probability. Approximate means that we are not going to get the exact joint probability, but we are going to have a good enough value. So for example, we are using a bigram model. So in the bigram model, we see here that if you want to predict the word K, the history you need to care about is the word K-1 only. So it's not the sequence from 1 to K-1, but only K-1. So if you want to predict the word number 5, you only need to care about word number 4. If you want to predict the word number 6, you need to care only about word number 5 instead of the sequence from word 1, word 2, word 3, word 4 up to word 5. So that's how we use the n-gram language model to approximate the joint probability. Now let's see a concrete example to compare the joint probability without approximation and the joint probability with bigram approximation. We are given here a sequence of words. Its water is so transparent, from word 1 up to word n. So n is 5 in this case. This is what we should calculate without approximation. So this symbol means the start of the sentence. Sometimes we put it here in the start of the sentence such that we can say the first word is the first word in the sentence given that we have the start symbol. And then the second word is water, given the history is start symbol and its. The third word is, given that the history is start, its, water. And then the fourth word is so, given the history is the start symbol, its, water is. Transparent, given the history is, which is getting longer, start, its, water is, so. So you see that the history is getting longer and longer, and so it's difficult to count. Sometimes we have not seen those sequences before. So that is without bigram approximation. Now contrast that with this bigram approximation. So we simply say the probability of its, given that the previous one is the symbol of start. Or in other words, its is the first word in the sentence. And then times the second word water, given the first word is its. Probability of is, given this previous word is water. And then probability of so, given the previous word is. Finally, probability of transparent, given the previous word is so. So you see here, using the bigram approximation, every time you just see a pair of words. Of course, it is more possible to find in your document probability of transparent given the previous word is so, compared to probability of the word transparent given that the previous sequence is exactly its, water is, so. So that's the advantage of bigram approximation. Using this bigram approximation, each of this probability is easier to find, is easier to compute in your corpus because the history is not too long. So you are likely to find that exists in your corpus. Again, if the history is so long, then you might never find it in your corpus. Remember, even in Google search, when the sentence is quite long, and then it will say that it does not find any result. So here's the comparison between computing the joint probability without approximation and with bigram approximation. Hopefully I made this very clear for you. We have seen that the joint probability using the bigram model approximation becomes like this. So to compute the probability of the word at position k, we just need to care about the word at the position of k minus 1. So to estimate these probabilities, it's quite simple. So in the bottom part here, you compute how many times, you count how many times the word n minus 1 appear. And then in the upper part here, you count how many times those two words appear together. So let's see an example where you want to compute what is the probability that you're seeing the word transparent given that the previous word is so. So in the denominator part, you count how many times you see the word so. And then in the upper part of the equation, you count how many times you see so transparent. So simply says that among all appearances of the word so plus x, how many times you see that so plus transparent appear among all possibilities of so plus x. X is any word. Okay, so you just calculate how many times the word so appear, and it is in the denominator. And in the upper part here, you compute how many times exactly so transparent appears. To do some practice on computing bigram probabilities, I provided you with 3 sentences here. And then, so first of all, if you have sentences, let's say you are collecting data or something, and then you put the start symbol at the start of each sentence. And then you also put this end symbol to say that this is the end of the sentence. So after you do that, you may start computing the bigram probabilities. So for example, these are some bigram probabilities, and you should be able to compute all these values. You may pause the video, take some time, and then ensure yourself that you can compute all these numbers correctly. This is a bigger example. So you see the first table on the top is the bigram counts from the Berkeley Restaurant Project corpus. It has actually 1,446 words, but then this table just shows 8 words of those. Now let's see, for example, what does this 827 means. It means that in that corpus we can count that the word I is followed by the word want 827 times. The word I is never followed by the word to, so this value is 0 here. And then this value is 9 because the word I is followed by the word eat 9 times in the corpus. Okay, so here it's just you just compute the frequency of the word in the row followed by the word in the column. And then the second table on the bottom simply computes the bigram probabilities. So what is done here is that each of this number is divided by the sum of all the values in the row. So you sum the occurrence of I and then followed by any of these words, and then you divide this 5 by the sum of all occurrences of the word I. So you get this 0.002. Same for the other values. So the sum of each row here must be 1. And then there are also some probability values provided here, which the purpose will be clear in the next slide. So I would like to ask you to do an exercise here. So use the data provided in the previous slide and then compute the probability of these 2 sentences. The first sentence is I want English food, and then the second sentence is I want Chinese food. Compare the probability, which one is bigger. So that's the end of the first part of this topic. And then in the second topic, I will start talking about how we can evaluate, let's say if we have 2 n-gram models and we want to compare which model is better, or how can we have a performance metric of a model.